and Professor Mironov and Professor Moronov, my collaborator in Moscow. So the contents are posted in archive articles, 3 articles. Unfortunately, our collaboration stopped around 2 years ago due to the pandemic of COVID-19. So in this workshop, we already have had 2 talks on Mach-Nernst polynomials by Yanagida-san and Yamaguchi-san. So my notation of Mach-Nernst polynomial is P lambda x qt, where lambda is a partition, x is a variable, and qt are 2 parameters. So I hope by the 2 talks in this workshop, you understand that Mach-Nernst polynomials are very interesting symmetric polynomials. So there are 2 features. First, they are orthogonal polynomials. And the second, they are simultaneous eigenfunctions or joint eigenfunction of mutually commuting Hamiltonians. So my topic is the possibility of deforming Mach-Nernst polynomials. And from the first point of view, so we can deform the inner product. As I'm going to tell you, this leads to a possibility of Kerloff deformation. On the other hand, the second point of view leads to another possibility, which I call non-Kerloff deformation. The reason I'm going to tell you later. So let me tell you about the second possibility more precisely. Maybe deformation in the product is already explained by Yanagida-san as a path from Shugo function to Jack and Mach-Nernst. So this seems more clear. But second point is maybe some confusing. So the Mach-Nernst polynomials are eigenfunction of mutually commuting Hamiltonians. So I'm not going to deform Hamiltonians itself, Hamiltonians themselves, but I'm going to deform eigenfunctions by looking at bispectral nature of eigenvalue problems. So this is related to some kind of duality of Mach-Nernst polynomials, which was also partly explained by Yanagida-san. So the bispectral nature of eigenvalue problem implies a possibility of existence of which I call Maser function. And I hope this Chinese character can be recognized by our Chinese colleague, right? Unfortunately, this in Japanese, this terminology is already taken as a Japanese translation of generating function. I don't know about the Chinese translation, but unfortunately, this terminology is already taken by generating function. So I'm not sure what is the precise or proper Japanese or Chinese translation, but literal translation is this function. I'm going to tell you why this function is important in the discussion of duality. So this Maser function, actually, this Maser function allows some formal power series expansion like hypergeometric series. So I'm going to deform this coefficient in a systematic way. This is what I call non-Kerloff deformation. So I don't deform Hamiltonians, but I will deform eigenfunctions. So this is my non-Kerloff deformation. So let me remind you about my notation again. So lambda is a partition. So this is non-increasing sequence of integers. And I will call, so at some point they terminate and this vanishes. So this last non-vanishing, the number L is, I will call the length of lambda. And McDonald function has two parameters, Q usually denoted by Q and T. And after deformation, we will have more parameters, 3, 4, and further. Okay. So first, let me start with some definitions. So symmetric polynomials in n variable, x1 to xn, is some polynomial which is invariant under the permutations of n variables. So this is invariant under the symmetric group Sn. So they form the ring, which I denote lambda n. Let small lambda a partition whose length is less than or equal to capital N, the number of variables. Then we denote x lambda. So the power of variable x and say xi is the integer lambda I. And monomial symmetric polynomials m lambda is a symmetrization of this x, or orbit sum of symmetric group Sn. So the fact is, the fact is, so let us denote the set of partition lambda whose length is less than or equal to n by p lambda, Pn. And then this set of monomial symmetric polynomials is a basis of the ring of symmetric polynomials. For example, these are examples of monomial symmetric polynomials. So I will denote the partition by standard Young diagram. So this is just one. So x lambda is just x1, and the symmetrization leads to this kind of symmetric polynomial. And in the same way, for example, this is partition 2, 1. So this part is this blue term. And after symmetrization, we get this monomial symmetric polynomial. I hope it is clear. So there are another kind of basis of symmetric polynomial, which plays an important role in the following. So which is called power sum symmetric polynomials, which is denoted by P sub n, is a sum of xi to the power n. So this is clearly symmetric. And for partition lambda, I denote P lambda as a product of this power sums. And also, the fact is this power sum symmetric polynomial is a basis of symmetric polynomials, but we extend the coefficient field from Z to rational numbers. For example, so if we expand monomial symmetric polynomials in terms of power sum symmetric polynomials, there appears some rational numbers as a coefficient. So we have to extend the coefficient field to rational numbers. As I told you, Kerov deformation is a deformation of the inner product. So the standard inner product on symmetric polynomial in terms of the power sum symmetric polynomial is this one. So power sum symmetric polynomial are orthogonal, and the norm of power sum symmetric polynomial is given by this combinatorial numbers. Yesterday, I suppose Yanagida-san defined inner product in terms of integral, which has some suitable measure. But I I think this is essentially the same as the inner product for sure polynomial. And we can deform this standard inner product in this way. So add this the lambda I, lambda J. So recall that lambda is a partition. So we have the sequence of integer lambda J from 1 to the length of lambda. And we suppose this factor depends on some parameters, typically Q, T, and further. Okay, so Keller function is characterized in the following way. So, but I call it Keller function, not polynomial. Unfortunately, again, there's some clash of terminology. Keller polynomials is already taken for different objects. So I will call this family Keller functions. So this is quite similar to the characterization of Macdonald polynomial and or Conway polynomial, which was explained by Yamaguchi-san. So first property is Keller functions are some triangular transformation of monomial symmetric polynomials. And then this coefficient, so this is triangular because there are some semi-ordering among Young diagrams or partitions, and only this, the coefficient are non-vanishing, only mu is smaller than original, this lambda in this semi-ordering. So this is the triangular property of Keller function. And the second is, of course, they are orthogonal. So by these two characterization and from the definition of this deformed inner product, we can find these Keller functions in just that way. So since this one column Young diagram or one column partition is a minimal element of this in this ordering, so they are not deformed. But for example, in the simplest case, this is 2, it is deformed. So here appears G1, 2, which is a deformation of this part. So an example, typically, so of course, in principle, the dependence on parameter of dependence on the parameters is in a sense arbitrary. But natural choice is the dependence on the parameter is rather in the sense of persistic. So this dependence of integer appears as a power, our powers of parameters. So this is typical choice of deformation Gn. So the product of, so we introduce parameters Q alpha and T alpha and deform the inner product in this way. So when kappa is 0, this is original inner product. And when kappa is 1, we have two parameters Q and T. So this recovers Macdonald polynomials. And if we take K, 2, 3, 4, then we have more parameters. For example, in the case of 2, we have 4 parameters. So this is a kind of the simplest, in the sense, the simplest example of Kerr deformation of Macdonald polynomials. Is it clear? So maybe I will skip. So this is some example of actual example of Kerf deformation, but let me skip this part. So let's move to the non-Kerf part. So the duality plays an important role in this kind of deformation. So first, let me review what was the Macnauer polynomials. So this Macnauer-Luthenauer difference operator already appeared in the talk of Yanagida-san. So we have some Q. So this is a difference operator acting on some symmetric polynomials, and then the meaning of difference operator is gamma I Q commute with variable x. So this is a kind of momentum variable, and then the Macnauer-Luthenauer difference operator of R's order has a product, R product of this difference operator, and this is some coefficient. When R equals 1, so this is a linear combination. So this is the first order in Q difference operator, and this is a linear combination of difference operator with n terms, and the coefficient is given in this way. So the famous fact is these Hamiltonians or Q difference operator are mutually commuting, and Macnauer polynomials are joint eigenfunction of these commuting Hamiltonians. Let me explain so-called bispectral properties of Macnauer polynomials. For that purpose, let me construct some generating function of these Q difference operators. So I introduce some indeterminate capital X and combine in the form of generating function. Then we have this kind of eigenvalue property. So recall this X is the indeterminate of this family of commuting Hamiltonians. So eigenvalues are here. So expanding this in capital X, we see what is the eigenvalue for each commuting Hamiltonian, dr. Then we can find the eigenvalue is a symmetric polynomial in y variable where y takes this form. And in the following, I will denote this. So it's a integer powers, integer monomials in Q and T. I will denote in this way. So by expanding this part in capital X, we see the eigenvalue is also again some symmetric, actually elementary symmetric polynomial in variable y. So this is what I call a bispectral property of this eigenvalue problem. So imagine that, so in a sense, this part is a kind of momenta, right? So we have some Hamiltonian, which is a difference operator in variable x. So this part is a kind of conjugate, this eigenvalue. So this is an eigenfunction, typically e to the something. Then this here appears some momentum variable. So we see, but of course, this momentum variable is quantized or discrete, like this. And eigenvalues are that symmetric function of this dual variable y. And also, we have some remarkable identity due to McNull. So this is typical some kind of quantization or discretization of variable. And again, so let us substitute this discretization to the original variable x. So this is also the identity which appeared in the Yanagida-san's talk. We see after substituting this discretization to not y, but x, we have a symmetry between of exchanging two partitions lambda and mu. Actually, this quantity represents some homological invariant of Hopplink. So from that point of view, the symmetry of lambda, symmetry in lambda and mu is quite natural. Of course, McNull derived this identity, not considering this not invariant, but actual thing is this identity is related to this homological invariant Hopplink. Okay, so originally we have as an eigenvalue problem, so we have this kind of special discretization in y variable, and discretization x variable implies the symmetry of exchanging lambda and mu. So all of these suggests the existence, and also there are some evidence from the knowledge of PL-time formula, but all of these evidences suggest an existence of mother function. So in my definition, the mother function is a function, or maybe it's a formal power series in original variable x and introduce conjugate variable y, which is symmetric in the exchange of x and y. And McNull function is recovered by substituting q to the lambda and t rho to y. So this is what was found in the eigenvalue problem. And the symmetry of mother function m, carry m, naturally implies this identity due to the symmetry in the exchange of xi. And actually, the answer, of course, all of these evidences suggest the existence of mother function. And actually, by Naomi and Shiraishi, shows we have actually mother function. And they gave quite explicit form of this mother function. So this mother function is a formal Laurent polynomials in variables x, and we take summation over these integers. Actually, so this is this parameterizes some positive cone of the root lattice of an. But yeah, actually, so just imagine we are given this data, and we take summation of this over this non-negative integers. So this mother function is a formal Laurent series in variable x. And we have quite explicit form for the coefficient, which I will give in the next slide. Please note that of course, in mother function hypothesis, we have symmetry in x and y. But the formula which they give, x in the formula, x and y appears quite asymmetric way. So this function is a formal power series of x, but here in the coefficient of this formal power series, the second variable y appears. And I'm sorry, this is, I just give you, we have quite explicit form of the coefficient y in this form. And here appears, so this is some ratio of this kind of quantity, which called Q-Hammer symbol. And if sorry, you remember the talk of Yamaguchi-san, this type of coefficient appears Q hypergeometric series. And so in the sense, this is multi-variable generalization of Q hypergeometric series. And what Nomi and Shirai showed is this is a kind of mother function property. So we need some correction term, which is x lambda to the lambda, but substituting q to the lambda and t rho to y variable, we can recover mother function. And to get symmetry in x and y, we have to multiply some function. So this is a kind of gauge transformation. And up to this gauge transformation, the mother function is symmetric in x and y. Okay, so maybe in 10 minutes, so I will skip this part. So this just gives some example of mother. In this slide, I hope to explain how mother function of Nomi and Shirai gives Macdonald polynomial, but let me skip here. So the coefficient of mother function given by Nomi and Shirai are product of this quantity. So this is what we call Q-Hammer symbol. And this is a ratio of this quantity, which is expanded in this way. So natural thing we try to deform is to introduce more parameter to this kind of function, which is already well known. So this has single parameter Q, but it is known we can have multi-parameter generalization. So let us consider the simplest case. So that let us introduce second parameter P and take the ratio like this part. So this is also a famous function, which is called elliptic gamma function, because this parameter, additional parameter P, has a meaning of elliptic parameter of some elliptic curve. Actually, there appears elliptic theta function, theta P. So our proposal of non-Kerloch deformation of Nomi-Shirai's mother function is to replace just this. This appears in the coefficient of mother function. Then we just replace this part to the ratio of elliptic gamma function. And actually, by using the relation of elliptic gamma function and elliptic theta function, the ratio is expanded in this way. So this is a product of elliptic theta function. More precisely speaking, this is a kind of elliptic theta function which is called odd. And additional parameter P has a meaning of elliptic modulus. So after this replacement, the triangular property is preserved. Actually, we can check after deformation, we have this kind of triangular deformation, and the only change is that this coefficient. I mean, this property is kept intact. Only changes the coefficient. Now, of course, this coefficient depends on additional parameter P, and this coefficient can be expressed in terms of this combination of theta functions, which I will denote zeta k, not gz, zeta k. It is very interesting that this deformation is expressed in terms of this special combination or special ratio of theta functions. So here's an example. So at level 2, I mean, the polynomial degree 2. So this is the ordering of the partition. And this part should be triangular matrix, triangular matrix in this ordering. So here is only non-trivial coefficient. And this is expressed in terms of this k is 2 and z is just 1. And in the next level, the polynomial has degree 3, and there appear two non-trivial matrix elements. And again, they are expressed in terms of some specialization of zeta combination of theta functions. So finally, here's an important issue. This kind of deformation does not necessarily guarantee the resulting polynomial is really symmetric. For example, in the next level, level 4, the number of boxes are 4. Here appears such a kind of terms after this kind of deformation. So this is clearly non-symmetric in X, right? So for Q hat lambda to be really symmetric, the coefficient F0 should vanish. So actually, F0 takes this combination. And we can check, actually, this vanishes by using some non-trivial identity of theta function. So in that sense, theta function appears in this combination is quite crucial for this property. Okay. Then finally, why we call this deformation non-Kellogg? The reason is the ring structure is qualitatively different. So product of symmetric polynomial gives again the symmetric polynomial. So we can expand in terms of this. And this is so generalization return of the Richardson coefficient. And here, so this polynomial has degree. The total the degree of this polynomial is equal to the total number of the partition lambda. So in principle, here appears the condition, just the condition is this. But from there is some selection rule coming from the representation theory. So this is a irreducible decomposition of the two representation tensor product. And from this decomposition rule, we have some selection rule. So here's some ordering of Young diagrams. Sorry, the partitions which satisfies this constraint. And the representation theory tells there are only a few non-vanishing coefficient here. So actually, Schur function, Schur polynomial and Magner polynomial satisfies. For Schur polynomials and Magner polynomials, there appears only a few non-vanishing coefficient. And by Kellogg deformation, we have some additional non-vanishing coefficient. But so there's some qualitative. So Kellogg deformation, the additional non-vanishing coefficient appears this range, which is allowed by which is a range which is allowed by this the property of representation theory. But for non-Kellogg deformation, we have some tail of non-vanishing coefficient, which is beyond the minimal one column partition. So in that sense, our non-Kellogg deformation is quite different from, in the sense, from the viewpoint of ring structure. Okay. This is my last slide. There are still, of course, many open problems. The first one is actually, in general, we have to use to prove that our deformation actually gives a symmetric polynomial for any partition lambda. Actually, I just give you some example, but so we only checked this is a symmetric polynomial up to level 5. So we don't have any general proof that actually this polynomial is a symmetric polynomial. So maybe the conceptual understanding of theta function identity is quite crucial for this to prove this property. And I emphasize the duality of original Magner polynomials. Then the natural question is, can the duality of Magner polynomial survive or not after this kind of deformation? It seems that at least one more parameter, W, is required. So this is not the deformation I explained today is not for keeping the duality. So of course we have some possibility. We expect we have some way to make duality survive, but I think I'm afraid this is beyond my talk today. So let me stop here.
Okay, thank you very much for your talk. Any questions or comments?
Sorry, I want to make some naive or strange question.
Yes.
In your talk, initially you start from some McDonald polynomial, so it looks like purely mathematics. But during your talk, suddenly you discuss about super selection rule. This is really physics, so I'm very confused. Why suddenly you have super selection rule? So
you are mentioning this part?
Yeah. So in this part, suddenly you discuss somehow.
No. This is just a representation theory. Of course, in physics, we can interpret this super selection, but this is purely some mathematics. I mean, in a sense, this is purely mathematics. That's some representation theory of general linear group.
I'm sort of confused. How to understand? How to define super selection rule in the context of mathematics?
No. Just decomposition of tensor product.
Yes, just tensor product. Yes. Then.
So then, if this, so in a sense, this partition, there's some correspondence between partitions and the representation of general linear group.
Yes, of course.
So this product corresponds to the tensor product in the representation theory.
Yes, I know.
Then here appears only some restrict representation appears here.
This is why this one is called the super selection rule.
No, I don't say super. You interpret this as a super. I just replace some, not super, but some selection rule. I mean, coming from
selection rule. I see.
Not super selection rule. I wouldn't say super selection. Just say selection rule.
Selection rule means that this decomposition, reduce decomposition.
Yeah.
So then my question
no. Maybe the simplest case is a representation theory SO3.
Yes.
SO3. Yes. Then this is just some rule for spin decomposition. So usually we say it's selection rule, no, in physics.
I have never used that terminology, so okay, now I understand. So in physics,
actually, in principle, I mean, from just some arithmetic, there is more possibility of appearing spins, but SO3 group restricts the possibility of spin after combining two systems, right?
Yes,
which I call some selection rule.
Limited number of
representation appears
in this situation.
Yeah.
So this one is called selection rule.
So this is what I called selection rule.
Oh.
And wouldn't say super selection rule.
Sorry, not super. Sorry, so I'm very confused. Sorry, I have a mistake. So okay, I understand.
And then, I mean, the point is after this kind of deformation, there's some contradiction with representation theory. There appears more non-vanishing coefficients.
Non-vanishing.
Any other? So any other questions or comments? If no, let's thank our speaker again.
Thank you very much.
the next talk
No,
starts.
sorry. So I'm supposed to be the chair of the next talk, right?
Yeah, I think so.
Okay.
So, Professor Kano becomes next chair, sorry.
So I'm sorry. So it's from
So in
a few minutes later. We have still have time to
4 minutes.
4 minutes, right? Okay. So Pan-san, can you try to share your slides?
Yeah. So can you see the slides?
Yes, fine. Okay, so let's start the second talk in the afternoon session. The speaker is Pan-san from Nagoya University. He will tell us McMahon-KZ equation for the quantum toroidal GL1 algebra. So please start.
So thank you, Kano Sensei, for the introduction, and I would like to thank the organizer for giving me a chance to speak here at the SUSTech-Nagoya workshop. It is my honor. So today I would like to talk about the McMahon-KZ equation for quantum toroidal algebra, and this talk is based on my paper with Kano Sensei that we published in the last year. Okay, so let's start. So the content of this talk will be divided into 3 parts. in the first part, I would like to give the introduction and motivation of why we are interested in the McMahon kinetic homological equation. And in the second part, I will give a quick review on the quantum toroidal GL1 algebra, its representation and the intertwiner. And in the part 3, I will derive the McMahon K-set equation based on the ingredients that I introduced in the part 2. So let's start with the part 1. Oh, sorry. Oh. So in 2009, Aude, Gayato, and Tachikawa had discovered the correspondence between the Nicholson factor of n equal to supersymmetric gauge theory on R4 with UN gauge group and the conformal blocks of the UN algebra. And then soon after that, Awata and Yamada lift this correspondence to the 5-dimensional version. Instead that the Nicholson factor of n equal 1 supersymmetric gauge theory on R4 cos S1 with the UN gauge group is equal to the conformal blocks of the Q deformation of the UN algebra. And then it's what's shown in the paper by Fakin and Shiraishi and many people that all of the Q deformed UN algebra can be generated from an algebra called the quantum toroidal algebra. So this motivates us to regard the quantum toroidal algebra as an algebra which underlies the 5-dimensional AGT correspondence. And one way to justify this statement is to consider the form K-set equation of the quantum toroidal GL1 algebra. So before explaining why this is a justification, let me explain what I mean by K-set equation for quantum toroidal GL1 algebra corresponding to some representation. So suppose that low be a representation. The K-set equation is the difference equation that take this form. So we have the difference operator act on the correlation function of the intertwiners, and that is equal to the product of the R matrix corresponding to the representation law multiplied with the correlation function of the intertwiner. And so we call the difference equation of this form the kinetic homological equation of quantum toroidal GL1 algebra. And you can see that the solution of the K-set equation is the correlation function. And as usual, we can write the correlation function in terms of the product of the conformal block. So if we can show that the correlation function can also be written as a Nicholson factor, then we get that there is some certain relation between these two objects, between conformal blocks and the Nicholson factor. So this justifies the statement that quantum toroidal GL1 algebra is the algebra which underlies the 5-dimensional AGT correspondence. And this is done in the paper by Awata and Kano in 2017. Okay. So now the goal of this paper is to derive the McMahon K-set equation and solve it, and then try to express the solution of K-set equation as the generalization of the Nicholson factor. So I will explain all the McMahon in the McMahon representation in the part 2, but for now you can just think of it as a generalization of the Fock representation. Then the question is why we are interested in McMahon. So here I will give 2 reasons. The first reason comes from the perspective of F5 Yangian, which is the rational limit of the quantum toroidal algebra. And from this perspective, the McMahon representation is more natural than Fock representation. The word more natural here means it appears in many physical contexts, physical application than the Fock representation. For example, in the higher spin CFT duality. And the second reason is that the McMahon representation preserves the S3 symmetry of the quantum toroidal GL1 algebra. S3 symmetry means the permutation of the deformation parameter. On the other hand, the Fock representation breaks this symmetry. So from these 2 reasons, I think it's natural to believe that the McMahon representation is more natural or more fundamental than the Fock representation. So now let's come to the part 2. So the goal of the part 2 is to introduce the notion of intertwiner of quantum toroidal GL1 algebra. However, in order to do this, we have to first discuss about the definition of quantum toroidal algebra and its representation. So let's start with the definition of quantum toroidal algebra. I set Q1, Q2, and Q3 to be the complex number whose product is equal to 1. And I assume that it satisfies the condition that if the product of Q1 power A, Q2 power B, and Q3 power C is equal to 1, A, B, and C must be equal. And then I define the quantum toroidal GR1 algebra to be the associative unital algebra with the generator EK, FK, K plus minus 0, HR, and central element C. And the index K run over the set of integer and the index R run over the set of non-zero integer. And these generators are subject to the defining relation. Here I just like two of them, but there are many others. And you can see that in the defining relation, I employ the current notation. I mean, I write it in terms of the current instead of write it in terms of the mode. This is because this allows me to write the defining relation very concisely. And we can show that the quantum toroidal algebra has the Hopf algebra structure. In particular, it means that it has a coproduct. And as we will see, the coproduct will appear in the definition of the interdeterminant. Okay, so let's talk about the representation. So the first representation that I am going to talk about is the vertical fork representation. So let F be the free vector space which has a set of partition as a basis. And we define the action of the currents of the quantum toroidal GR1 on the set of partition as follows. From this explicit formula, you can directly check that it satisfies the defining relation of quantum toroidal algebra. So it forms a representation, and we call it the vertical fork representation with the spectral parameter V. And we can explain this action in terms of the diagram. And in terms of the diagram, the action of EZ and FZ is just adding and removing a box from the diagram. So to illustrate this, let's consider an example. Lambda is 3T1. So in this case, we if we add on the partition T1 by the EZ, we have to add a box in two of each line. So we obtain the following diagram. However, if you use the formula explained in previous place, you can show that the coefficient of the single diagram is 0. This is in accord with the fact that this diagram is no longer a partition because partition must be decreasing, but here this is increasing from 3 to 4. So the coefficient in front it should be 0. And similarly, if we add on this partition by the current FZ, we have to remove a box from each line. So we obtain this diagram. Again, the coefficient of the first diagram should be 0 because this is not a partition. Okay, so we have talked about the fork representation. So now we come to the second one called the magma horn representation. And the magma horn representation can be considered as a generalization of the fork representation. This is because the representation space of the magma horn representation had a set of plane partition as a basis. The plane partition is just the partition with the multi-layer. So if you look at each layer, you will obtain a partition. And similarly, we can have the formula for the action of the current on the set of plane partition, but because the formula is quite complicated, so I didn't write it explicitly here. But from the explicit formula, you can just check that it satisfies the defining relation of quantum toroidal algebra. So it forms a representation, and we call it the magma horn representation. And it is important to note that the magma horn representation now depends on two parameters, the spectral parameter V and an additional parameter K. And this comes from the fact that indeed, I mean, we can construct the magma horn representation from the infinite tensor product of Fock representation. And because we do the infinite tensor product, we need some regularization. And during the regularization process, the parameter K appear. And similar to the Fock representation, we can explain this action in terms of the diagram. So for example, let's consider the plane partition 2, 1. It means that the first layer is the partition 2 and the second layer is the partition 1. So if we add on this plane partition by current EZ, we have to add a block into the diagram. So if we add a block here, we obtain this partition. If we add a block here, we then obtain this plane partition. And if we add a block here in the second layer, we obtain this plane partition. And then if we add a block in the third layer, we obtain this plane partition. But we cannot add a block here because if we add a block here, the higher layer will be bigger than the lower one, so it's no longer a plane partition. Okay, so the final representation that I going to introduce is the horizontal Fock representation. So suppose that A be the operator we satisfy the Heisenberg algebra, and we define the vector space H to be generated from the negative mode operator acting on the vacuum state 0, where we define the vacuum state to be the state that annihilated by the positive mode operator. Then if we define the action of the currents like this, we can show that it is a representation of quantum toroidal algebra, and we call it the horizontal Fock representation of level 0. Actually, by using the horizontal Fock representation of level 0, we can generate the horizontal Fock representation of higher level by defining the action like this, and we call it the horizontal Fock representation of level n. You can see that if we substitute n to be equal to 0, we just get the horizontal Fock representation of level 0 in the previous plane. Okay, so we have introduced all the representation. So now we are ready to give the definition of the intertwiner. So let V be a Fock or magma horn representation, and H prime be the horizontal Fock representation. So a Fock intertwiner or the magma horn intertwiner depends on what V is. It's a map from the tensor product of V and H to the H prime, and this map must satisfy the intertwining relation here. And because the Fock and magma horn representation, because we know that in the Fock and magma horn representation, the generator HR and HS is commute. So their axes are simultaneous eigenbasis of this operator. So I denote it by set alpha. And actually, for the Fock representation, this alpha is just the partition, the set of partition. And in the case of magma horn representation, this set of alpha is just the set of plane partition. And for each element of this set, I define the alpha component intertwiner to be this. I mean, just substitute just fix the element of B to be the alpha. So this is called the intertwiner. And by solving the intertwining relation, we can show that the Fock intertwiner and magma horn intertwiner must take this form. But we don't need to remember this formula. I just like here because I just want to point out that if we take the plane partition lambda to be the partition, and if we take K to be the QT, the magma horn intertwiner will reduce to the Fock intertwiner. And we call this the 2D partition limit. This 2D partition limit is very important when we want to find when we want to interpret the solution of magma horn K-sub equation as a generalized Newton factor. Okay, so now we have already introduced all the ingredients. So let's start deriving the magma horn K-sub equation. First, recall that the difference equation of we call the magma horn K-sub equation if it takes this form, as I have explained earlier. So what we want to do now is just to find the equation that take this form. So now if we add on the McMahon interdeterminer by the operator Q minus square V del by del V, then we obtain a McMahon interdeterminer whose spectral parameter V is scaled by Q square, Q minus square. And then we can write the scale interdeterminer in terms of the new operator called T operator, T plus minus operator, and the original one, or original McMahon interdeterminer. And because we know the explicit form expression of the McMahon interdeterminer, we can lead the expression of the T plus and T minus operator. And we can show that if we move the T plus minus operator through the McMahon interdeterminer, it will generate the McMahon R matrix, which is first calculated in the paper by Awata and Kano using the method of universal R matrix. It is important to note that if you use another scaling parameter here, I mean, rather than the Q plus minus square, the T operator will not generate the McMahon R matrix. So here, the Q minus square here is the only possible parameter that this will be happen. Okay, so now we define the correlation function of the McMahon interdeterminer into this form, by this formula. And if we add on this function by the operator Q minus square Vi del by del Vi, then we get that the spectral parameter Vi must be scaled by Q minus square. And as I explained previously, we can rewrite it in terms of the shift operator, T operator, like this. And if we from this formula, if we move the T plus to the right and T minus to the left, it will generate the McMahon R matrix. So if you consider this, you can see that this is in the form of the McMahon K-set equation. So this is what we want to find, right? And now we are going to solve it. And we define the 2-point correlation function like this. And we can show that if we define the function G to be this function G will satisfy the McMahon K-set equation. And if you consider the inverse of the 2-point correlation function and take the 2D partition limit that I explained previously, you can see that it is equal to the Nicholson factor up to some proportional factor. So this means that we can regard that the inverse of the 2-point correlation function as a generalized Nicholson factor. I believe that the McMahon K-set equation and the generalized Nicholson factor should be related to various objects in field theory and string theory. But for now, we still don't know what object that is related. But I leave this for the future work. So this is end of my presentation. So thank you very much for your kind introduction, your kind attention. Thank you very much.
Okay, thank you very much for your talk, Alfonso. So are there any questions or comments?
Well, can you remind me this McMahon the KZ equations? Is it in the CFT context? What is the meaning in the CFT context?
What is the meaning about the KZ equation?
Yeah, it's originated from KZ equation, right?
Yeah.
But yeah, I don't know. I just probably want to know what kind of a CFT or string theory associated to this. Do you know that?
I don't know that, but
okay.
Okay, so probably I can tell you an answer. So vertex operator in CFT is a kind of intertwiner,
Okay.
right?
Yeah.
And so he considered the correlation function of intertwiner for quantum toroidal algebra, not quantum affine algebra.
Okay.
So
Okay.
in that sense, the equation should be called KZ.
Okay.
Does it answer to your question?
Yeah, kind of. Yeah. Yeah.
Okay. So first, I just think that you asked the physical meaning of the equation. So
Yeah,
I
I
don't know.
also want to use origin, but quantum toroidal, it's
Yeah.
into what it is. Yeah.
Yeah. Because I mean, in CFT, what we usually find is affine real algebra and quantum affine algebra, right? But the quantum toroidal algebra is I don't know. Yeah.
I see.
Are there any questions?
Can I ask one question?
Yeah.
So it is related to Professor Kong's question, but can you take the differential limit or some trigonometric degeneration of this McMahon-Kayes equation?
So you ask if you take the
initial limit, then
we will get the
do you have any solution of that differential equation?
I have never done that, but I think we can. I mean, we can do it. I mean, we know that if we take the trigonometric limit of the quantum toroidal, we get the alpha yang GL1, right? So I think if we take the limit of the McMahon-Kayes equation, it should be some equation of the alpha yang GL1. But I have never done that, but I think it can be done. Yeah.
So some conformal block-like object for affine Yangian GL1 should be the solution of that degenerated.
Yeah.
Thank you very much.
Yeah, thank you very much.
Any other questions, comments? Okay, if not, let's thank the speaker again. Thank you.
So thank you very much.
So next talk will start at 3:50 in Japan time. I mean 2:50 in Chinese time, right?
So can I try?
Yes, please,
translate it?
Minami-san.
Thank you.
Yes, that's fine.
Oh, thank you.
So, okay, let us resume the afternoon session. Our next speaker is Professor Kazuhiko Minami from Nagoya, and he will tell us algebraic generalization of Jordan-Wigner transformation and its applications. So please start.
Thank you. Thank you. First, I would like to express my thanks to the organizers for inviting me today to give a talk. So today I will explain a new method to diagonalize Hamiltonian and obtain the free energy exactly. In this method, we can find solvable Hamiltonians and transformations that diagonalize each Hamiltonian from series of operators that satisfy a specific commutation relations. By this method, the Hamiltonians are transformed into the free fermion system. A lot of important models can be diagonalized by this method, namely the one-dimensional transverse Ising model, or type chain or cluster model, XY model, or two-dimensional square lattice Ising model. And an infinite number of solvable Hamiltonians can be also obtained. We can also diagonalize the honeycomb lattice Kitaev model with the Ventoric code interaction and find that anion excitations appear. And we can also obtain generators of the Onsaga algebra from our operators. So at first, let us consider generally the diagonalization of Hamiltonians. We want to obtain the partition function exactly. So if we can diagonalize the Hamiltonian, we obtain the eigenvalues, and then we obtain the partition function without any approximation. One way to diagonalize the Hamiltonian is to transform the Hamiltonian into the free fermion system. The traditional transformation from spin systems to the fermion system is the Jordan-Wigner transformation here. So the Jordan-Wigner transformation has been used as a basic tool of this area. Today in this talk, we will introduce a non-trivial generalization of the Jordan-Wigner transformation based on commutation relations. At first, we will explain our fermionization formula, which is the main point of today's talk. Let us consider a series of operators here. We consider the case that they satisfy the commutation relation here, written here. Eta j operators, eta j and eta k anti-commute when they are adjacent, and otherwise they commute each other, and square of each eta j is equal to 1. So then the following Hamiltonian is solvable. This is eta j, and kj is a coupling constant. The transformation to diagonalize this Hamiltonian is explicitly given here. Then phi j, this phi j satisfy this anti-commutation relations, and they are commutation relations, and they are the Fermi operators. So we obtain the Fermi operators. So
sorry, what is this kj?
kj is a coupling constant. So eta j is operators, interactions, and kj is some constant.
Okay.
But this includes, of course, this includes data. So this includes temperatures, constants over kT.
Okay, thank you.
Okay. So let us consider an example. This is the transverse Ising model. So I found this new formula when I tried to find new way to solve this basic model. This is the Hamiltonian of the transverse Ising chain, and this is the Ising interaction, and this is the transverse field term. And we consider the series operators here. They are the local Hamiltonian. The Hamiltonian is composed of these operators. So this is the Ising interaction and transverse term, and physically different. They are physically different, but let us forget the difference of these two and consider the commutation relations. So this sigma to x anti-commutes with this term and this term, because sigma to x and sigma to z here anti-commute with each other, and this sigma to x commute all the other operators. And this Ising interaction anti-commute with this sigma to x and sigma 3x and commute with all the other operators. And the square of these operators are equal to the unity because they are the Pauli operators. So let us introduce new notation eta. So this is eta 1, eta 2, eta 3, and they satisfy this commutation relation, and we have a series of operators that satisfy this condition, and the Hamiltonian is now written here. So operators and external field and coupling constants. So, but this relation depends on J, and is not convenient to solve. So let us introduce a product of operators like this phi j. So I cannot explain why we consider this product, but I will show that this product works to diagonalize Hamiltonian. We consider the product phi j, and then we find that they anti-commute for all j and k here. But we also find that the square of this phi j shows an additional sign here. So let us redefine phi j like this. This is a normalization factor, and this is a phase factor. Then we find that they satisfy this relation and this anti-commutation relation, and we find this. We find the Fermi operators here. This is the explicit form of the transformation in the case of this transverse Ising model. So phi j explicit written here. We will also introduce an initial operator eta 0. We don't need eta 0 to diagonalize the Hamiltonian, but the calculations become simple with this eta 0. So then the transformation to phi j is explicitly written here. This is nothing but the Jordan-Wigner transformation. So we obtain the Jordan-Wigner transformation in this case. In the case of the transverse Ising model. So the Hamiltonian is written by two-body products of phi j. Here, this is because the eta j is proportional to this product, and because the Hamiltonian is a sum of eta j. And we can introduce the cyclic boundary condition here. We consider the boundary terms and classify them, and the cyclic boundary condition appears. Now the model can be diagonalized by standard procedure. We now have the translational invariance, so we will introduce the Fourier transformation. Here CQ satisfy the anti-commutation relations, and they are the Fermi operators. And the Hamiltonian is written by CQ like this, and this is the two-body terms of the Fermi operators, and they can be diagonalized. The Hamiltonian is expressed by the matrix form. Each matrix is 4 times 4, corresponding to each wave number q, and we can diagonalize the total Hamiltonian in diagonalizing each 4 times 4 Hamiltonian. Diagonalization procedure of this small Hamiltonian, corresponds to the Bogoliubov transformation. So we find the eigenvalues here and can be obtain the partition function here, and the free energy is written here. This is, of course, identical to the free energy of this model we already know. So this is a summary of this formula. The first step is to find the series of operators eta that satisfy this commutation relations. They anti-commute with its adjacent operators and commute with all the other operators, and the square of each operator is the unity. Then the following Hamiltonian can be diagonalized. We can diagonalize this Hamiltonian by this transformation. Usually we have a Hamiltonian. When we have a Hamiltonian we want to diagonalize, we have to try to find the transformation to solve it. But in this formula, the transformation is automatically obtained from the series of operators, from the Hamiltonian. This is the basic idea of our new fermiionization. Then the structure of this talk is simple. From now on, I will show you examples of Hamiltonians that can be obtained, and diagonalized by this formula. First, let us consider one-dimensional quantum spin chains. This is the simplest case. Here, X denotes the Pauli operator sigma X, and Y denotes sigma Y, and Z denotes sigma Z. This is the interaction sigma X, sigma X. This is sigma Y. And these two operators anti-commute because of this X and this Y, and commute with the other operators. And the square of each operator is equal to unity because they are the Pauli operators. So this series of operators satisfies the condition. The solvable Hamiltonian obtained from this series is written here. Then we introduce the Fourier transformation and obtain the eigenvalues and the partition function and the free energy. This is the case with the period 2. The series of operators satisfies the condition, and the coupling constants have the period to K1 and K2 and K1 and K2. This model is sometimes called the one-dimensional Kitaev model. The Hamiltonian is written here, and the eigenvalues and partition function here. So we obtain the free energy, which is identical to the free energy of the transfer sizing chain here. The reason is now clear. Both the one-dimensional Kitaev model and the one-dimensional transfer sizing model have the coupling constants with the period 2, and there remains no difference when they are written by eta. Here, this is a Hamiltonian. Two Hamiltonians are identical when they are written by eta, and we need only the commutation relations to solve the models. And the period is 2, so their free energies are identical. This is a case with the period 3. The eigenvalues are obtained from this equation. When we consider the case with K1 equal to K2 equal K3 uniform case, the system reduces to uniform case. In this case, the equation can be solved explicitly like this. We find 8 solutions, and the partition function is obtained like this. This is identical to the first case. So this is a case with the period 4. The Hamiltonian is written here. The partition function is expressed by the eigenvalues, which are the solutions of these equations. The calculations for period 3 was complicated, but period 4 is much easier. Next, we will introduce 2 series of operators here, the blue line, this blue line, and the red line here. Each series satisfy the condition, and 2 series commute with each other. Then we have the interactions like this. This is a model which we call the XY chain, but the XY chain with general interactions K1, K2, K3, K4, and general external field H1, and here we external field is H2, H1, and H2. So let us solve this general XY chain. The partition function is written by these P and Q, and they are written by A and B, and A and B are written by the interactions. When we consider the uniform case here, K1 equal to K4, K3 equal to K2, and uniform external field, then we obtain the well-known result, classical result obtained by many authors. Next, we show new models which can be solved by this method. let us consider the cluster model. The Hamiltonian is given here. This XZX is the cluster interaction. And sometimes we add the interactions Y, ZY, or YY, and they can be solved by the Jordan-Wigner transformation. However, when we introduce this term, this next nearest neighbor interaction, xj plus 2, then the model cannot be diagonalized by the Jordan-Wigner transformation. However, the series of operators here, our series of local Hamiltonians, satisfy our condition. So this model can be solved by our new formula. The transformation is automatically obtained from the Hamiltonian. The transformation that diagonalizes this model is shown here. This transformation is somewhat complicated and clearly different from the Jordan-Wigner transformation, but it diagonalizes this Hamiltonian. This is the list. This list is the Hamiltonians which locate. This list is the Hamiltonians which locate near the cluster model and which can be solved. These are not all. I didn't try to list all the solvable models. They are examples. For example, the transverse. For example, the transverse Ising chain, the XY chain, and the cluster model belong to this first Hamiltonian. Here, n is an arbitrary integer, and L is also arbitrary. So this Hamiltonian includes an infinite number of solvable interactions. So next class is a generalization of the XY chain. The XY chain is a special case of this first Hamiltonian and also a special case of this second Hamiltonian. We have, for example, 10 series of Hamiltonians and one additional Hamiltonian. Each series contain 10 series contain infinite number of solvable models. So each solvable series can be generalized again. The local Hamiltonian is a two-body product of phi j here. Here we consider the case j and j plus 1. In this table, we consider phi j and phi j plus 1. But when we introduce the phi j and j plus L, the model is still solvable. So this is a list of the generalized Hamiltonians. All of these interactions are solvable. Transverse Ising model and XY model and cluster model belong to this case, and they are diagonalized by the Jordan-Wigner transformation. In the first table, we considered j and j plus 1, and they are generalized to j and j plus L. These are solvable interactions, and this is the transformation that diagonalizes them. Next, these interactions are XX and Y corresponds to j and j plus 1, and these are the generalized interactions. All of them can be solved, and this is the transformation to solve this Hamiltonian. The cluster model with the next nearest neighbor interaction here belongs to this case, and the cluster model with another next nearest neighbor interaction, this sigma j, z, and sigma j plus 2 z belongs to this case. These cases cannot be solved by the Jordan-Wigner transformation, but these models are also solvable by our formula. We can find other solvable interactions here, or like this. These are summarized in this paper. So next, let us consider two-dimensional systems. Let us consider the two-dimensional square lattice Ising model. This model was solved by Onsaga, and one of the most important models in statistical physics. The model consists of Ising interactions on the square lattice. Let us consider a generalization, the interactions with the period M. They vary with the period M. The Hamiltonian is here. Here, the partition function is written by the transform matrix. The transform matrix of this model are written here. So then here we find the interactions of transverse Ising chain, Ising interactions and transverse term. So we will try the transformation that diagonalize the transverse Ising chain. Then the operators are written here by two body products of the Fermi operators CQ. They commute each other. Then it is easy to diagonalize the transform matrix. The partition function is then decomposed into small matrices. A and B are given here, and we need the maximum eigenvalue of the transform matrix. This is obtained from this block. And the free energy is obtained here. So at last, we set the period M equal to 1. Then we obtain the free energy of the square lattice Ising model derived by Onsaga. Next, we will consider the two-dimensional honeycomb lattice Kitaev model with the Venn-toric chord interaction. The Kitaev model consists of the two-body interactions XX, Y, and Z, sigma Z on the honeycomb lattice. This model was introduced by Kitaev and the ground state is specified. The Venn model was introduced by Venn, consists of four-body interactions, and this model is equivalent to the toric chord model, which was introduced in connection with the quantum computation. Today, we will consider the honeycomb lattice Kitaev model with these three-body interactions, and with these four-body interactions. And these two are the interactions of the Venn model. For the purpose to compose and solve this model, we need, most important thing is to find a series of operators that satisfy the condition and that generate the interactions of this model. For the purpose to have the Kitaev model, we introduce this series of operators. This is sigma Z and Ising interaction and sigma Z. This is a series for the transverse Ising model again. And on the next row, we again introduce the same series. Then we automatically obtain a transformation. In our case, the transformed phi is shown here. Pauli spin operator sigma Z on these sides, and the last operators is sigma X or sigma Y. This is also phi J prime sigma Z on these sides, and the last operator is sigma X or sigma Y. The anti-commutation relation is now obvious. These Z and these Z commute with each other. And this omega is sigma X or sigma Y, anti-commutes with this sigma Z. and the rest are identity here and commute with each other. This is a Jordan-Wigner transformation in 2 dimensions. So we have a series of operators and we have a transformation. I won't go into the details of the calculations, but all the interactions are expressed by our phi with the use of the conserved quantities like this. We can compose all the interactions we need, and they, for example, this is constant. This is a conserved quantity. The 3-body terms are obtained similarly, and we can introduce solvable 4-body interactions. These are the interactions of the Venn model. They are reduced to 2-body products of phi and can be diagonalized. For example, the product of this and this is equal to 1/2, this and this 1/2, and the product of these 2 are fixed, and finally we obtain 2-body product of phi's and can be diagonalized. After all, we obtain the honeycomb lattice Kitaev model with these 6 kind of 3-body interactions and these 4-body interactions, which are the interactions of the Venn model. The model can be diagonalized in the subspace in which we can find the ground state. And the ground state phase diagram is obtained exactly. This is a ground state phase diagram. Here, X corresponds to the set of interactions, and Y here, set of interactions Z plus and Z minus. And upper half of this diagram corresponds to the positive KZ, and the lower half corresponds to negative KZ. And L here is the 4-body interaction, and here L equal to 0. This is a case solved. This is a case solved by Kitaev. And black region are the gapped phase, and the white regions are gapless. And we introduce non-zero L, and L becomes larger, and in this case, L equal to 1. Next, we consider the symmetry of the system. The Hamiltonian is invariant under this change of signs of interactions, together with a rotation in spin space. So these 2 are equivalent. We also consider the change of signs of momentum. Then we find these 2 are identical as an operator. And also consider some shift of the momentum. We find these 2 are identical. We use these symmetries in the next slide. Then let us consider the generators of the anyon excitations. The anyons are generated by an external field and string operators. According to the symmetries explained in the previous slide, we can show that when we change the signs of interactions, operator phi j are transformed to other phi j in other location, and the generators of anyons change its location, but still they are generators. Still they generate anyons. We know that anyon excitation appears in this phase. Then we can conclude from the symmetry another anyon appear here in the transform phase, and we find the anyon excitation appear in each phase. Next, let us consider the relations with other transformations. First, we will formally show the that the Jordan-Wigner transformation is a special case of our formula. Let us consider phi 1 and phi 3 that are introduced when we solve the XY chain. Let us consider a canonical transformation in which Fermi operators are transformed into new Fermi operators. Then the coefficients U3 and U1 should have this form. Here, theta is arbitrary. Then we set theta equal to j minus 1 pi and choose negative sign. Then we have this transformation. This is nothing but the Jordan-Wigner transformation. So the Jordan-Wigner transformation is obtained from a specific series of operators and from a specific canonical transformation. So this is a special case of our formula. Next example is the transformation by Nambu. Nambu solved the square lattice Ising model in 1950. This is the first result of him and the second or third paper of him, in which he introduced a transformation. The inverse of his transformation is a transformation we introduced, a special case of the transformation we introduced when we diagonalize the XY chain, except that the definition of the initial operator and the phase factor is different. So algebraic structure. Let us consider algebraic structure. At last, let us consider the algebraic structure of our formula. Our series of operators eta has a relation with so-called the Onsaga algebra. When Onsaga solved the square lattice Ising model, he introduced the operators an and gn here. These operators satisfy the commutation relations here. This is so-called the Onsaga algebra. The Onsaga algebra appears in the structure of the square lattice Ising model, and for example, in the structure of the Kyler-Potts model and in related one-dimensional quantum spin chains. We introduce a series of operators etas, which satisfy our commutation relation. Then now let us define an and gn here. And generally, let us introduce an and gn here in terms of our operator eta. Then an and gn satisfy these commutation relations, and thus they are generators of the Onsaga algebra. So we find the relation with the Jordan-Wigner transformation, generalized Jordan-Wigner transformation, and the Onsaga algebra. So this is the summary of my talk. So thank you very much for your attention.
Okay, thank you very much for your interesting talk. So are there any questions, comments?
Can I ask some questions? I don't have a specific questions on the content because, but I find the talk is very interesting. So I was wondering where to find the reference. You show the reference on the nuclear physics B, but I searched. I didn't search. Oh, okay. Just give me here.
Okay. Thank you very much for your interest. This is you can also find these reference in the abstract of this conference.
Oh, so you have a so if I find the last one, I should be able to have everything in the reference list, right? So
yes, especially this website, you can find all.
Okay, I see.
Any other questions? Comments?
Well, I probably have some other questions for in physics. There are many different kind of dualities, different from the Jordan-Wigner move. Your theory can say something about those dualities, which is not Jordan-Wigner type, because Jordan-Wigner type looks like a switching bosonic degree of freedom to the fermionic one. But what about others?
So at present, I checked the relations with the Jordan-Wigner transformation or classical transformation by Nambu, but I don't have any additional idea, so still this might be open.
Okay.
Any other questions?
Can I have a question?
Yes, please.
So you have stated that the first step is to find the set of operators eta, right?
Yes.
And I want to ask that, is it in general easy to find these eta, or finding this eta is non-trivial, and after we found these etas, we can just apply your general method?
I tried to find many etas like this and this and this. It is not always quite easy, but we can find many etas, and because we need only the commutation relations, the etas doesn't need written by the spin operators. Eta can be general operators, provided they satisfy the condition.
Yeah, so they are, so the eta themselves like form like an algebra, right? Something
Yes.
like an algebra.
So that's right. So they relates to the Onsaga algebra. So like this. Eta itself is a general operator and generate the Onsaga algebra here.
Okay. So if we are given an Onsaga algebra, can we obtain these etas? Or yeah.
I don't think so. But inverse is right. If we have eta, so we can find generators of Onsaga algebra.
Okay, thank you.
No. I think the question was is it easy to find etas, right?
Yeah.
Yes.
And
I have...
sorry. The answer is
not quite.
Not quite.
Not quite difficult.
Not quite difficult.
Sorry, I think there are two questions. The first question is that given a Hamiltonian that can be solved in your way, and is it easy to find those etas? And yeah, that's my first question.
In the first case, the Hamiltonian can be solved by this method when the local Hamiltonian, the interactions in the Hamiltonian satisfy our condition.
Maybe one more time. Sorry.
So,
Get.
sorry.
For example, are there any general prescription to find eta?
So this Hamiltonian is written here. So the local Hamiltonian and the interaction is written eta j. And when these eta j satisfy this condition as a series of operators, this Hamiltonian can be transformed to the free fermion system by this transformation.
Yes, I get that. And I think the chair and I are still wondering that if we are given a Hamiltonian, a concrete one, and this Hamiltonian can be solved in your way, the question is it easy to find those etas? Is it easy to define those etas?
If you have some Hamiltonian and if you try to solve this by this method, you should decompose the interactions to satisfy this condition. So if you find the explicit form of eta j, then you can find the transformation.
Yeah, so maybe my question is not a very good one, and I want to know that is it a easy process to determine those eta, or is it highly non-trivial from a given Hamiltonian to this decomposition into etas?
I probably could answer, because it looks like this should be easy. Yeah, because I think he already explained that you just split the Hamiltonian into terms and see if they make this works. I think in most cases it's not so hard.
So it is easy in these simple cases. So this is eta and eta 1 and eta 2 and eta 3. But possibly there exists more complicated cases, but can be solved by this method. So, but this most simple and basic case eta is directly these local Hamiltonians interactions and easy to find.
Okay, thank you both. I have another question. Is there a general rule to determine whether a Hamiltonian can be solved in this way?
I don't know. I always try each Hamiltonian to solve by this method. So I don't have a good answer at present.
Okay, I see. Thank you very much. Your talk is very interesting.
Okay. Any other questions? Comments? So if not, let's thank the speaker again. Thank you very much, Minami-san.
Thank you.
So Minami-san, can you take the role of chair in the next talk?
Yes. I am supposed to the next year. I know that. So I think it's time. So let's start the next talk. The next speaker is Professor, I don't know, but how Zhu, is that right?
Sorry, I'm not a professor. I'm a PhD student at Göttingen. Yeah.
The pronunciation, how your name is Zhu. So from Mathematischen Institut Georg August University, Göttingen. So title is Higher Representation Theory of Finite Group. So please.
Okay, so before I start, let me thank organizer of this conference and chairing person for introduction. So my name is Hao Xu. Today, my talk is about higher representation theory of finite group. So we will start with some basics from classical representation theory of finite groups. So let's fix an algebraically closed field K of characteristic 0. We define the group algebra for a finite group G to be the vector space spanned by elements of G together with the following Hopf algebra structure. So this multiplication is induced by group multiplications on G. The multiplicative unit is induced by group unit. Co-unit here is given by copying of group elements, and co-unit here is given by augmentation of algebra. And finally, there is an antipode given by taking inverse of group elements. Once we have the group algebra, we define a G representation just as a left module over group algebra. And the homomorphism between G representations is a homomorphism between corresponding left modules. So let's denote the category of finite dimensional G representations as rep G. Okay. Now let's consider this bilinear pairing on group algebra. This bilinear pairing is non-degenerate and G invariant. Therefore, suppose M is a G submodule of our group algebra, then its orthogonal complement turns out to be a complementary G submodule. So our group algebra is finite semisimple. And that is equivalent to say rep G is a finite semisimple linear category. Moreover, we have an additional symmetric monoidal structure on rep G induced by Hopf algebra structure on Kg we defined. So in details, monoidal product of two representations is defined to be tensor product of their underlying vector space with an induced G actions, which exactly corresponds to the coproduct on Kg. And monoidal unit is given by one-dimensional subspace K with trivial G action. And finally, associator unitars and half braiding are just the same as those for tensor product of vector spaces. This symmetric monoidal structure on RepG induces a non-negative integer coefficient algebra structure on the set of isomorphism classes of simple objects. So these are simple G representations. And we will refer to this algebra as the representation ring of RepG. To study the representation ring, we need the character theory. So a function on group G is a class function if it is invariant on the conjugation G action. Given the finite dimensional G representation, we define its character to be just the trace of corresponding G actions. Group characters have following properties. First, it is additive in the sense that it sends direct sums into a sum of class functions. So by the way, characters are by definition class functions. Second, taking character is multiplicative in the sense that it sends tensor product to pointwise product of class functions. And finally, it takes dual representations into an antipode composed with character of original representation V. As a consequence, you see the algebra of characters is a representation ring of RepG, but with coefficients extended from non-negative integers to the whole field K. Then we need to prove a powerful lemma called fixed point formula. Suppose U is a G representation, then we can consider its a submodule of G fixed points. And let's consider a linear endomorphism on U, defined by taking average over elements lying in the same G orbit. This turns out to be a projection linear map, i.e., if you apply pi twice, this is the same as apply pi only once. And the image subspace of this projection map is exactly the submodule of G fixed points. Therefore, we can compute its dimension to be the trace of this projection map pi. And it is by definition taking average over values of this group character of U. With fixed point formula, now we can prove a very central result in classical representation theory of finite group, which says irreducible G characters form a basis for all class functions on G. Now we first show that it is a linearly independent subset. The way we prove is, let's consider the pairing, the bilinear pairing defined as follows. Then we compute pairing of two irreducible G characters. And then we apply various properties of characters we just mentioned. And here we apply fixed point formula. Okay. Now let's take a look at this space. This space is G fixed point of linear maps from U to V, but that is by definition a space of a G representation homomorphisms from U to V. And finally, we apply Schur's lemma to obtain the result. So this implies irreducible characters are linearly independent. Then we need to show the irreducible characters is a maximal linearly independent subset. By Artin-Wedderburn theorem, we know the number of isomorphism classes of simple modules for a finite dimensional semi-simple K algebra equals the dimension of its center. So in this case, our group algebra is finite dimensional semi-simple. And what is its center? Well, its center turns out to be isomorphic to the algebra of class functions. So that finishes our proof. In summary, we see there is a one-to-one correspondence between simple objects in rep G, so simple G representations, with basis elements in center of group algebra. Okay, so this is a quick recap of classical representation theory of finite group. Now we are going to see the real categorification of representation theory. Here I have a table summarizing the key ingredients throughout this talk. You see the left column is various structures we just go through in classical representation theory. And the right column is a corresponding categorifications of these. So let's briefly go through them. So group algebra KG will be categorified to the category of G-graded vector space and G-graded linear maps between them. This is a tensor category with tensor product induced by group multiplications on G. And in addition, there would be a kind of categorified Hopf algebra structure, which I will not go into details here. Then we can consider its category of module categories. So its module categories and module functors and natural transforms forms a linear two category, which we treated as two category of two representations of G. It is also equipped with a symmetric monoidal product given by the Lin tensor product of linear categories. So this is kind of categorified notion of a tensor product of vector spaces. Then center of algebra is categorified to the notion of Drinfeld center of a tensor category. So it is a naturally braided tensor category. In our special case, Drinfeld center of vec G, it has an explicit description given by the category of G-graded G representations or G-graded G equivariant vector spaces. The tensor product on this category is a kind of tensor product of G representations, but with a twist on grading, which has something to do with conjugation action of G. And we just see irreducible G characters forms a basis for class functions. And in the later half of my talk, we will see this result also has a categorification. And the categorified notion for irreducible G characters is the notion of so-called Lagrangian algebras in center of vec G. So let's recall some important types of algebras in braided monoidal category B. We say an algebra in B, it consists of an object A together with multiplication M from A tensor A to A, and a unit goes from monoidal unit I to A, and they should satisfy the associativity and unitality conditions. Furthermore, an algebra is said to be commutative if it satisfies an additional commutativity constraint. Then we say an algebra is separable if you can find a section of multiplication, which is AA bilinear. So AA bilinearity is equivalent to the following Frobenius conditions for delta. Okay. Oops. Given an algebra A in B, a left A module in B is an object M together with a left A action rho goes from A tensor M to M, which satisfies the associativity constraint and the left unity constraint. Similarly, we can define right A modules as follows. Then a left or right module homomorphism is just a morphism between underlying object which commutes with the corresponding left or right A actions. Okay, so let's denote the category of finite projective left or right A modules in B using this notion or this notion. A fundamental result in the theory of tensor categories is important here, so I list it. It first appears in a 2003 paper of Ostrich, which says, so given an algebra A in tensor category C, the category of right A modules has a natural left C module category structure. So C acting on the left on these module categories. Conversely, with some mild finiteness conditions, every left C module category is of this form. In particular, one C is a finite semi-simple category. A left C module category is finite semi-simple if and only if the corresponding algebra is separable in the above sense. So when B is a braided tensor category, we say it is indecomposable if category of right modules is indecomposable as a left B module category. Okay, now we have various examples. The simplest example is in category of vector space VEC. By Artin-Wedderburn theorem, we know a separable algebra in VEC is just a finite sum of matrix algebras. Moreover, if you require it to be indecomposable, then you just have a matrix algebra. A slightly more interesting example is in RepG. An indecomposable separable algebra in RepG is always given by internal home of some simple G representation V. In particular, if our simple G representation V is one-dimensional, then its internal home is just a trivial one-dimensional G representation. Okay. Then Ostrich in the same 2003 paper provide a classification theorem for indecomposable separable algebras in RepG. So the classification is given by pairs H phi, where H is a subgroup of G, and phi is a two group cocycle on H. So remember, this result will be used later. We define an Italic algebra to be an indecomposable commutative separable algebra in B. We also have examples in category vector space. By Artin-Wedderburn theorem, a commutative separable algebra is a finite sum of matrix algebra of size 1. So it's finite sum of trivial algebra case. Hints up to isomorphism. If we only require it to be indecomposable, then the only Italic algebra you get is just the trivial algebra. Okay. A more interesting example is, let's consider in a RepG, a commutative separable algebra, right? In RepG, let's first forget its G action, then it has an underlying commutative separable algebra in VAC. So by the last example, it is a finite direct sum of trivial algebras. And then it should be equipped with a compatible G action. Hence, we can pick a basis closed under this G action, and this basis forms a finite G set. Now the condition of indecomposability says this basis must be a transitive G set. So in a sense, it is a coset space. As a result, an Italian algebra on RepG is isomorphic to the function algebras on coset space. So that is the classification result. Davidov, in his 2010 paper, provide a classification for Italian algebras in string field center of VAC. So this is given by triples H, N, and phi, where H is a subgroup of G, N is a normal subgroup of H, and phi is a kind of group cohomological data. In particular, when H equals N, this group cohomological data is just a 2 cocycle on H. So in this case, the corresponding Italian algebras are called Lagrangian algebras. So compare this result with the result of Ostrix, we see simple objects in 2 RepG, which by definition are Morita classes of indecomposable separable algebras in RepG. They are in one-to-one correspondence with the Lagrangian algebras in center of VAC. So it justifies the table that Lagrangian algebras is kind of categorifications for irreducible G characters. Okay, I think my time is up, so thanks for listening.
So, are you finished?
Yes.
Maybe we have some time more. This is the last talk.
So the following are just references.
Okay.
Yeah, I think it's a good place to stop. But of course, the story doesn't end here. So due to the length of time, I don't have time to introduce these various categorical notions in details. But you see, the next story should be considered categorical level 2 and higher, right? And this is a current topic under investigation, which also has a lot of interesting things, but we don't have time to discuss here. So, yeah.
Okay.
Are there any questions?
Okay, thank you very much for your talk. So, any questions? Could you show some examples concerning physical systems such as quantum mechanics or spin operators?
I'm not an expert on this physical interpretation, but what I heard is that so you can treat dream field center VAC as a kind of categorical data corresponding to the 2+1D digraph-Witten model with the trivial twisting. And in there, Lagrangian algebras gives you a kind of, so condensations of these Lagrangian algebras gives you kind of boundary conditions for this 2+1D box theory. And of course, this can be realized by lattice theory. Yes.
Yes, thank you. Any questions? So it's time. So I will close this session. Thank you very much for your nice talk.
Thank you very much.